Hi, welcome to lesson 15D, the quotient rule. The goal of today's lesson is to learn about differentiating quotients of functions. Over the past few days we've looked at the chain rule and the product rule, and now of course we'll do the quotient rule. And the quotient, just to remind you, quotient is the division of two functions. So if we've got u of x and v of x, then u of x is divided by v of x, and we have to make sure that v of x does not equal 0, otherwise this would be undefined. And so then if we take the derivative of q of x, what we do in this case is we're going to take the derivative of the top, so u prime of x, multiplied by the bottom, v of x. Then we're going to subtract. In the product rule we added, but in the quotient rule we're going to be subtracting. Then we take the u of x just as it is, and we multiply by the derivative of the denominator, v of x. And all of this is going to be over v of x squared. Okay, if we look at it another way, we can say, well, if y is u divided by v, again, v cannot equal 0, then dy by dx is u prime v minus uv prime all over v squared. So let's take a look at a couple examples of the quotient rule and how that works. Graphing of functions is a big thing in calculus, and a lot of times graphing of rational functions leads to kind of interesting looking graphs, and so you may be faced with taking derivatives of quotients or rational functions in order to find different characteristics of graphs that you'll be asked to find, to graph, or sketch, I guess. So one example we have here, we've got f of x equals 5, start off something simple here, 5 over 4x cubed plus 4. And so we have to make sure that that denominator does not equal 0. So we can just state that. If we were more interested in finding exactly what values of x would make the denominator 0, we'd have to rearrange and solve this in order to find which values of x could not be included in this denominator. But just for this instance, we're just more interested in finding the derivative using the quotient rule. So when I take the derivative here, I take the derivative of the numerator first. That gives me 0. And I multiply that by the denominator. Then I subtract the numerator multiplied by the derivative of the denominator, and 4x cubed, the derivative of that is going to be 12x squared, and that's going to be all over the denominator squared. It's very important that you have these things in the correct order because of the subtraction. That'll change things completely. So you don't want to take the numerator and multiply it by the derivative of the denominator and put that in the first term, because then when you take the derivative of the numerator and multiply by the denominator and have that as the second term, that's the part that's going to be negative then. Okay, so it has to be in this specific order. And then we just simplify briefly here. Of course, 0 times this is just 0, so we're left with negative, and I guess I can just multiply those two together, so negative 60x squared all over 4x cubed plus 4 all squared. Okay, so I'll just stop there. You could do some factoring or something along the way maybe. Right now I'll just leave it. Other quotients, other derivatives or gradient functions may lead more nicely to factoring. So then you can simplify down a little bit before you find things like turning points, etc., and points of inflection, which we're going to look at in chapter 16. Okay, so moving along to example 2. Let's say y is 4x cubed minus 3x squared, and that's over 4x to the power of 5 minus 4. And dy by dx, again, take the derivative of the numerator, and it's 12x squared minus 6x, and we multiply that by the denominator. Then I subtract, keep the numerator as it is, so 4x cubed minus 3x squared, and multiply that by the derivative of the denominator, which in this case is going to be 20x to the power of 4. And then that is all over the denominator squared. Okay, again, is there factoring, are there factoring opportunities here? Yes, there are, but just for this example, I'm just going to leave it as is, like that. Okay, so we could factor out here a 6x, we could factor out a 4 here, factor out an x squared from this, okay, and then see what we can simplify down. But for now I'm just going to be dealing with the derivative itself. And then for the last example, f of x is 3x plus 1 to the power of 4, so we're going to be incorporating the chain rule now, over 3x cubed plus 5. Okay, so when we have something like this, we have to do the chain rule inside the quotient rule. So as we go about taking the derivative using the quotient rule, when we take the derivative of the numerator, which we're going to do first, we're going to be utilizing the chain rule for that. Okay, so the derivative of the numerator, well, with the chain rule, we're bringing the 4 down in front, leave the bracket as it is, and subtract 1 from the exponent. Then we go inside and take the derivative of the inside, which in this case is just 3. So all of that is going to be multiplied by the denominator, which is 3x cubed plus 5. Okay, so this part is the u prime x, and this is just the v of x. And then we're going to subtract, and I'll keep the u of x as it is here. So that's the second part of the rational function, and the derivative of the quotient rule. And then we take the derivative of the denominator, which is negative 9x squared. And then all of that is going to be over negative 3x cubed plus 5 all squared. Okay, like I said, we can do some more simplification. So what I would normally do at this point, I would at least put the 3 and the 4 together. I'd maybe put this negative 9x squared to the front here. I usually bring all the short or the small factors to the front. Then here I could factor something out, perhaps, between these two terms I could factor out 3x plus 1 to the power 3 from both these terms, bring that outside, and that can just kind of help a little bit, and then maybe we can expand in the bracket that's left over and maybe factor that. Some of these things kind of can be expanded and then factored again to make the curve sketching a little bit easier at the end. Okay, but those are 3 examples of the quotient rule. We'll look at a few more tomorrow in class, and until then, please take a look at page 370, example 8, and then take a look at questions 1 ACDF, 2 AC, 3 and 4, all from pages 371. So thanks for watching, and we'll see you in class.